I'm standing here outside this admittedly generic and boring looking building in Austin, Texas. But inside, IBM develops and tests power servers. Now the lab is usually off limits to everyone except the core team, but I got us a special invite to check it out. Follow me. Wayne, thank you so much for having us today. I'm excited for you to show me around this data center.
It's not a data center.
Okay, what is it?
It's a system integration and test and development center for our power systems.
Okay, what does that mean?
This is where we put all the systems together for the first time, put the power supplies, the backplanes, the chassis, memory, processors all together. We're the first ones to turn it on. We'll do what we call a system power on,
Okay.
and then check for smoke.
And by check for smoke, you mean make sure that nothing's broken?
Correct. We run soup to nuts. All the testing you can possibly do to make sure that the customers are getting the most reliable server that they can possibly get.
I love that. I'd love to see what you got. Can you show me?
Let's go.
So, as you can see, there's a noise warning for this lab inside. Right now, about 65 decibels. It's about to get a lot louder. Although I can barely hear them over the sound of hundreds of enterprise-grade systems buzzing away, whoa, it's really loud in here. Wayne explained that this is one of the labs where the reliability and availability of power servers are tested. That includes checking both firmware and software integrations. In essence, IBM scientists and engineers run these power servers nonstop at their limit to monitor for performance dips. This rigor helps them build machines that businesses can rely on for their most important work, even when they encounter extreme conditions. And that takes us to our next stop. Where are we now with these things?
This is called the guard band. This is where they do the external testing on the system. We'll run it through extreme heat, extreme cold, voltage, high voltage, low voltage, and make sure that it'll always continue running. So our reliability is what a customer expects.
Okay, it's basically a torture chamber for servers.
Yeah, you could call it that.
Like one of these big things here.
Yeah, in fact, that's one of our small ones.
This is the small one.
I've got a bigger one back here.
This thing here.
Yeah.
Whoa, it's massive.
Right now we're doing a cold testing on the Power E1080.
Cool.
Check it out.
It's freezing in here.
Yeah.
How cold is it?
Right now it's 10 degrees C. It's probably going to go a little bit colder than this.
Okay.
But the servers have to run at cold temperatures.
So you basically leave it in here, turn on the ice, and get it as cold as possible to make sure that they can run in a row.
Still got to run. Actually, they like it colder like this.
Okay.
But they need to run when it gets really cold.
And in the same chamber, can you also turn up the heat so you test for heat?
We're going to go probably up to 85 degrees in here.
Wow. What other type of testing are you putting these servers through?
We also do earthquake testing for systems that are going to go to California, where they might be subject to an earthquake. We also do RF testing, where we subject the system to RF signals and also try to see what kind of RF signals come out. Then there's the noise testing too. How much noise is actually coming out or put out by the system versus how much noise it can take.
It sounds like you got to consider a ton of things when you're like designing an architect.
Oh yeah.
Is there someone I can talk to about that?
Well, Kava's our main engineer, so he'd be a good one to talk to.
I'd love to meet Kave. All right, Kave, so this is the E1080 server, right?
Yes, that's correct. So this has 4 Power 10 processors, but E1080 comes with multiple flavors. Customers could order it up to a 16-socket system, which means 4 of these stack on top of each other.
4 of these big boys.
And then cable up together from the back.
Gotcha. Let's take a look inside.
Before we do that, let's put our static.
Oh, okay. And what are these for?
These are to make sure we discharge our body to the system so we don't harm any electronics.
Cool. I don't want to break anything, so let's do
right.
that. Let's get set here.
Okay. We got our 4 processors here.
So these 4 things are processors.
No. This is a heat sink. This is what cools the processor.
Okay.
Underneath the heat sinks, we actually have 4 of these. This is the actual Power 10 E1080 processor.
Okay, so this is like the brains of the server.
This is the brain of the system, yes.
And what's special about this Power 10 processor here?
Actually, inside what you're holding, it's actually a Power 10 chip.
Okay, we're getting smaller and smaller here.
Right. So this is based on a 7 nanometer technology, and there are 18 billion devices into what you're holding right there.
18 million or billion?
18 billion devices.
18 billion devices on this chip.
Correct.
That's amazing. So what are some of the unique properties of the chip?
So we have a built-in AI inferencing inside the chip. And it's about 5x faster than what our previous generation Power 9 processors have.
Not bad. And what does AI inferencing do for the user?
It's used for machine learning.
Okay.
And in other systems for machine learning, you use GPUs and FPGAs. You have to transfer data from your processor to somewhere else, get it processed, and move back. In our processor, everything is done on the processor itself.
So they don't have to move the data as far, so it's faster and it's more reliable.
Correct, and also a lot more secure because you're not moving the data somewhere else to get processed and come back. These are actually cables to bring the signal from top of our processors, bring the high-speed signals out via these cables to the back of a system. And that's how we are connecting 4 of these systems
Gotcha.
to each other.
So when they're stacked on top of each other, comes out through this, through
The
the back of the
high-speed
system.
signal comes directly from top of a processor, which we are the only one in the industry is doing that.
Wow.
Goes through these copper cables, internal cables, go through an external cable like this,
Through the
and
back
go
here.
to another node. That's how we manage to connect 4 of these together to create one gigantic 16-socket system. Another really important part, our memory subsystem, we have a buffer chip in our memory.
Okay.
And every single communication between the processor and the memory is fully encrypted through the hardware. Also as a spare DRAM as well, so if there's any of these DRAMs that you can see, if there's any of them fail, it will actually can switch to spare and keep going without losing any performance, without the system coming down. And because this system, it's all about reliability and availability, we have an extra power phase on all the DIMMs.
Very cool.
And this system, fully loaded, can have up to 64 terabytes of memory.
64 terabytes, that's a lot.
That's a lot. And because of that, and because of the performance the system provides, we actually hold the world record for SAP HANA, the largest SAP HANA database that's certified. It's run on this system.
Wow.
In front of the memory, we have all the regulators. These are VRMs, or what we call voltage regulators. Every different component in the system use different voltages.
Okay.
So the regulators like this brings the 12 volt down that our power supply generates to different voltage levels that other components need. Because this is our most reliable system, every single regulators, they're N+2 phase. That means there are 2 extra phase
Wow.
just sitting there as a backup, just in case anything goes wrong. System automatically switches to the backup and keep going. And there are other components here in the front as well. For example, this is our clock card. This card generates reference clock for the processor and the memory for different components in the system. And if you notice, there are 2 of them identical. And the reason for that is, again, this is our most reliable system. For every single component, there is a redundant one, a backup, a spare.
So there's a lot of stuff going on in here, and I think it gets pretty hot. I know we got the heat sink, but we also have fans up front.
Correct. In the front of a system, we have 5 fans assemblies. These are all concurrently maintainable. What that means is while the system is up and running, if there's any issue with any of the fans, we can service them without the system going down, while the system is up and running.
So everything you and Wayne have showed me today means this machine is super powerful, it's super reliable.
Yes, that's correct. You can do a lot of work with a lot less of these machines. So because of that, you can have a lot smaller carbon footprints. Things that you could do potentially with 100 servers, you could do probably with 2 of these.
So you're lowering your carbon footprint and probably doing some cost savings as well.
Of course, you save cost by less power getting used, and also for licensing. Typically licensings, they get charged by how many core you have. And because this machine can do a lot more with a lot less system, a lot less cores, you save a lot of money from licensing fees as well.
So what's next for you guys? What are you working on now?
So we're already working on next generation of these systems.
So no rest, no downtime, you're already doing the next generation and you're gonna look to beat the records you set with this one.
Of course.